this is the circuit that has been implemented using several ways of using various Verilog constructs. Okay, well, not that we covered all the details of Verilog constructs, but we did see several different formats. And now what we are doing is focusing more on RTL components. And we talk about data components, and then we talk about controllers. About data path components, are like multiplexers. We have already seen a good number of them. Flip-flops, counters, full adders, registers, ALUs, and so on. So all of these components that we are showing here will be described using the formats and the constructs that we are already familiar with in the earlier part of this lecture. So let's start with the multiplexer, and this is an 8-bit multiplexer. The symbol for it is something like this. Let me perhaps draw it a little bit nicer. An 8-bit input, an 8-bit input. This is called data 0, data 1. The output is 8, and then there is a select input and the output is called bus 1, and the select input 0 puts A in, on the output, and select input being 1 puts the other input. Okay, so if this is 0, this goes on the output. If this is 1, this goes on the output. Okay, what's different? Well, nothing except this square brackets 7:0, meaning the inputs are 7 to 0, or index 7 to 0, meaning that the inputs are 8-bit vectors. And the keyword input applies both to data 1 and data 0. If you have another input that is not of this size, let's say 3-bit input, then you have to have another input, then the square bracket, then the other input name. And I'm using an assign statement here. Usually if you have timing, you also include the time scale here, which in this case I don't. When we get to a test bench, we will have timing there as well. Let's describe a flip-flop. This is a flip-flop. Notice that I'm using different input-output format. Here I use input-output right on the declaration on the header part. Here I'm using the inputs-output list here in the header part, and then declaring them like this. So my inputs are reset, DN, and clock. This is the flip-flop I'm doing. This is the flip-flop I am doing. It has a negative edge, and this is C1, 1D, 1R. This is the reset, and this is the Q output. This is the clock input. This is reset input. This is this is the clock input. This is the in, and this is Q out. Okay, this is what we are describing, and this is a negative edge trigger synchronous reset flip-flop. Let's read it. On the negative edge of the clock, flow begins in this always statement. When flow begins in this always statement, right after the negative edge of the clock, if reset is 1, during that negative edge, then a 0 goes into Q out, and if reset is not 1, then D in goes into Q out. Okay, and therefore this becomes a flip-flop with the input with reset, active, high reset, and this is synchronous reset. That means reset is only looked at during the rising edge of the clock. Something that we have seen before but we didn't discuss is the fact that everything on the left hand side of assignments and kind of assignment in Verilog inside always statements must be declared as reg, and therefore you are seeing Q out declared as reg here. Okay, just take it as a rule that if you have something on the left hand side inside an always statement, it has to be declared as reg. Something else here, notice that before I showed you various descriptions, and also I showed you the multiplexer in using an always statement, I use this assignment. Here I'm using an assignment which is an arrow. This is called a non-blocking assignment. I use non-blocking assignments for registers, and I use this, which is called a blocking assignment inside the always statements for combinational circuits, as we will be seeing. Okay, so that's a simple flip-flop, and this is the symbol next to it. And yeah, this is where I'm talking about the fact that the signal has to be declared as reg if it is to receive a value inside an always statement. The always statement is said to be sensitive to the negative edge of the clock, meaning that it wakes up only when you see a negative edge of the clock. And again, these are the assignments that are non-blocking assignment. Let's describe a counter, and I have a 4-bit counter. It's a modulo 16 counter, and inputs and outputs are declared up here, unlike this, that inputs and outputs are only listed up here, and then the declaration of the mode, whether it's input or output, and the size, and whether it's reg or not reg, comes here after the header part. Usually this, the counter, is the format is the more preferred one. I could of course also include reg over here, and if not, then this is also one way of doing it. Why do I declare count as reg? Because my intention is to give it an assignment or give it the value or put it on the left hand side inside an always statement. An always statement runs forever. It waits for sensitivity so it waits for, in this particular case, negative edge of the clock. Once it finds the negative edge of the clock, flow begins. As soon as the flow begins, it looks at reset. If reset is active, means 1, then it puts 4 zeros inside the counter. This is the number format for B0. That means take binary 0, expand it to 4 bits. For decimal or hex 0 means that this is the hex 0 expanded to 4 bits. And you can also use decimal, and if you have long stream of numbers, you can use underscore to separate various digits to make it a little bit more readable. In any case, what is happening is on the rising edge of the clock, reset is looked at. If reset is 1, put zeros inside the counter. If not, come to the else part. The else part takes the old count value, adds a 1 to it, puts it back into the counter. That means on the falling edge of the clock, or negative edge of the clock, if reset is not active, then counter increments by 1. And then it waits for the next edge of the clock. What we are describing here is a modulo 16 counter. It is an up counter. It is a counter that has a active, a synchronous reset, and it is a counter that performs count up on the falling edge of the clock. Alright, so this is my counter, and let's keep going with more components. And notice that I'm also using non-blocking assignment, meaning this arrow. Again, see that I'm using anything on the left hand side is declared as reg, and the always block here is describing a sequential circuit. Just repeating, just reminding. I'm going to describe a full adder, and the full adder can be described by two Boolean expressions, and the full adder is this actually: A, B, Cin, okay, and then this is my sum output, and then here is A, B ANDed together, A and Cin ANDed together, B and Cin ANDed together, or together, and that becomes your carry out. This becomes your sum, and therefore what you have here is a full adder with a sum output with a carry output, and then I'm using one Boolean expression for the sum, one Boolean expression for the carry out. Okay, just to show you that there are various ways of describing hardware in Verilog. And this is a combinational circuit, and I can use several of these, let's say 8 of these, in this fashion. Carry out, sum 0, sum 1, and then the carry out from 1 into the carry in of the next one to build, let's say, a 4-bit, an 8-bit, or whatever number of bits I need for my adder. So carry in, the initial carry in is carry 0, becomes 0, and let's call this one carry in is a 0, and this is A0, B0, A1, B1, A2, B2. This is the final carry out, and then this becomes carry 0, this becomes carry 1, and so on. All right, if you want to have multiple of these, therefore you can instantiate several of these to build a bigger adder. Let's do a shift register. Again, another possible data path component. The shift register is this. It has a left shift. It has a right shift. It has a clock. It has an 8-bit input, parallel input, and it has a 3-bit mode input. Okay. Serial left, serial right, a 3-bit mode input, M1, M0, taking value 0001, 1011. It has a clock. It has 8 bits of parallel input, pair in, 8 bits. It has 8 bits of pair out. Okay, and this is a shift register. Okay, not a shifter only, it's a shift register. What it does is the following. If mode is 00, it does nothing. Doing nothing means that it just takes the old pair out, puts it back into pair out. If mode is 01, it right shifts, meaning that it takes the left coming input and uses that as bit number 7, and all the other bits of pair out will be shifted one place to the right. If the mode is 10, it performs that was right shifting. This is left shifting. Left shifting means that it takes serial right from the right, puts it into bit number 0 of the pair out, and all the other bits will be shifted one place to the left. If it is 1-1, if mode is 1-1, it takes whatever is on pair in and puts it on pair out. Okay, how do we describe this? The way to describe it is write an always statement. The always statement waits for the negative edge of the clock. If clock arrives, then look at M. I can do if-else statements, but what I'm trying to do now is to use a case statement. The case statement says if M is 0 or 1 or 2 or 3. If it is 0, take par out and put it back into par out, do nothing. If it is 1, take the SL, concatenate it to the left of par out 7:1 and then put that into par out, and therefore this is a right shifting. And if mode is 2, meaning that it's 1 0, then take the serial right and then put it inside curly brackets. Curly brackets is for concatenation, and put par out 6:0 to the left, SR to the right. That forms an 8-bit vector. Clock that into par out, and then this becomes the shifted or left shifted output of the shift register. And if it is 3, means that you are doing parallel input, and therefore pairing clocks into the pair out, just like a register. Register, what it does is on the clock, it puts data in into the data out, and this is the same functionality as that. And this is declaration, so I have 8-bit input pairing, then I have a 2-bit input M. M is used as a case choice, and these are the case alternatives. This is doing nothing. These are shifting right and shifting left using curly brackets. This is doing parallel loading. I have one more thing here to do, and that is default. Default means that just in case, if none of these cases are true, M is not 0, 0, 0, 1, 1, 0, or 1, 1. How can it be not true? Well, if it's, for example, it has a bad value, it has an X on it, it has a Z on it, then none of those are true, and therefore in such a case, what you want to do is just do nothing, and or reset it to 0, or do something that indicates that an error has happened. What I'm doing here is I'm putting 8 X's on my par out. That is if M receives a value which is not 0, 0, 0, 1, 1, 0, or 1, 1. And default is a good thing to put in case statements. It's not required, but it's good to do that. And shifting right and left happens when mode is 1 or 2, and curly brackets are used, concatenation operation is used. I'm using case statement again here for describing an ALU. This is an ALU with, again, I have a mode input, but this mode input selects one of the 4 functions of the ALU. The ALU is an 8-bit ALU having the left input and the right input. I'm using, again, I'm using an always statement. Let's read this. It says always when right or left or mode change, begin the process into the always statement. You begin and then you look at the mode. Something has changed. Look at the mode and then see if mode is 0 or 1 or 2 or 3 or none. If it is 0, perform adding. 1, perform subtracting. 2, and the 2 right and left together. 3, or the 2 right and left together. If it's none of them, then again you want to put 8 X's on your ALU output. Alright, what else to be said about this? Well, the output is reg, and it is a 8-bit vector, and it is declared reg because I'm using it inside a case statement. Because I'm using it inside an always statement on the left hand side. I'm using this kind of assignment versus this, okay, because this is combinational circuit and this one is sequential, a sequential circuit. This is called blocking. This is called non-blocking. And the format, I'm using output reg here. I'm using output reg here. Okay. And this is really the preferred way of describing your inputs and outputs and the sizing and everything, even though there are alternatives that I've shown you how to use as well. And I talked about this, blocking and non-blocking, and the default is when something goes wrong and your mode is not exactly what you expected. We have covered several functions and several components, an ALU, a shifter, a multiplexer, and all that, all of which go inside a data path of an RT level design, but then these components have to be connected like this. Okay, what if I have the multiplexer and ALU to be connected? In that case, what I do is I write a module, maybe my data path module, declare my buses and everything, and then I instantiate this module and this module within my data path and perform or make the connections between them. To make the connections between them, anything that carries data have to be named or declared. And therefore what I do is, maybe this is an input bus coming from the outside, maybe these are buses coming from other parts of the data path. I have to declare all of these, and then I use this kind of construct. This is called component instantiation for declaring the instantiating and wiring the two components. Let's read what it says here. It says in bus connects to the left of ALU. Let's look at ALU. ALU has a left input, and therefore here is saying the in bus that is visible in this description connects to the left named input of the ALU. AB input, which is probably declared in this environment here, connects to the right named input of the ALU. Okay, out bus connects to ALU out. ALU out is supposed to be name of a vector or a signal inside the ALU, and mode, as we saw, is also declared inside the ALU. The description here, which connects my in bus to left, AB input to right, or out bus to ALU out, function to mode. This is called port connection by naming or named port connection. And I'm doing the same thing for the multiplexer, named port connection. Alternatively, I could do ordered port connection. That means I don't need to specify the name of the ports of the ALU or the multiplexer here. All I do is I just use this ordering, which is supposed to be the same ordering as the ports as the ALU to which these signals are being connected. And therefore I have two alternatives: named port connection and ordered port connection. And in most cases this is the preferred way, because if you mix the ordering, doesn't matter, and because you have to have the correct name, and if you don't use the correct name, the Verilog compiler will raise it as an error, so you know that there is something wrong here. If you mix these and put them in the wrong order, maybe something it is possible that if the sizes matches and all that, Verilog is not gonna complain, but then you're gonna get bad description. All right, we have covered every component of the data path. Now let's talk about the controller. What is a controller? A controller is a part of the circuit that makes decisions, and as it makes decisions, it goes from one state to another. As it makes decision, it issues signals, and like control signals, and it actually looks at its inputs from outside world or from data path to make transitions from one state to another. So that flowchart really describes my controller, but I'm not going to describe controller using a flowchart. I will be describing my controller using a state diagram. Let's do an example. First of all, a controller is a big thing. A controller for a processor may have 20-30 outputs and then 20-30 inputs. But see, I'm not going to be doing a big controller. I'm only going to do a very simple controller, and one with only one input, with only one output, and just 4 states. I'm just going to show you the format for describing components. And for that, I'm going to be using a sequence detector. You probably have seen sequence detectors in logic, and this is what I'm describing here. A sequence detector is a circuit that has one input, one output. It looks for a certain sequence of ones and zeros on its inputs, and then puts a 1 on the output when the certain sequence has been detected. So let's do the sequence detector. The circuit I'm doing is this. I'm looking for 110 on my input A. If 110 is found, then my output becomes 1 for a complete 1 cycle, and then remains 1 for a complete clock cycle, and then becomes 0. That's it. This is a sequence detector. Let's see how I code it in Verilog. It has an input A, it has a clock input, and it has an output. The way it works is the following. I have a clock. Okay, and these are clock pulses, and let's say I'm doing positive edge of the clock. Okay, if in 3 consecutive clock pulses I find 110 on my input, the output becomes 1 and remains 1 for a complete clock cycle. A 1, a 1, a 0, and a 1, a 1, a 1, a 1, and a 0, a 1, and a 0. Okay, what happens to my W? Well, here I'm seeing a 0 on my A, I'm seeing a 0 on my A, I'm seeing a 1, I'm seeing a 1, I'm seeing a 0, I'm seeing a 0, I'm seeing a 1, I'm seeing a 0, I'm seeing a 1, a 1, a 1, a 0. Okay? If in 3 consecutive clocks I find 110, my output becomes 1 for exactly 1 clock period after the rising edge of the clock, leading all the way through the next rising edge of the clock. And then again, 110 becomes 1 and then becomes 0 with the next rising edge of the clock. Okay, let's make sure that I have covered everything. Yes, so this is what I expect from my circuit. To do this circuit, I need a state diagram, and the state diagram is developed as such. Wait for the 1 on A. Once you find the 1 on A, go forward. Okay, wait for another 1, and then when you find it, go forward. When you get the 1 and then you get a 0 following that, you go to the state where the output is 1. Okay, so the way you do it is you say 110, go forward, fill in the sequence, and then go back and fill in the blanks. To fill the blanks, this is how you do it. You say, well, if I know I get a 1, I go forward in the state S0. What if I don't get a 1? If I get a 0, that means nothing useful has happened. Go back to this state. In the state S1, if a 1 takes you forward, what if you get a 0? A 0 means that you have received a 1 and a 0 following that. Well, that's not good because you were looking for 110 and not 10. So let's go back and start over. In the state S2, you are looking for a 0 to go forward. What if you get a 1? Well, if you get a 1, sure, you didn't get the 110, but you still have the two ones that you have received. So let's say that another one takes me back to this state, and I keep looping back in this state. Once I'm done with 1, 1, 0, then you have a 0, meaning that 1, 1, 0, another 0, 1, 1, 0, 0 together doesn't give you any sequence, and therefore you go back to the 0 state. If you get 1, 1, 0, another 1, you say, well, I received 1, 1, 0, and then this next one is the beginning of perhaps the next 1, 1, 0 sequence, and therefore you go to the state where a 1 has been saved, and this is where you go to state S1. This is the state diagram, and now let's talk about the coding of this state diagram in Verilog. This is how you will describe it. Okay, let me start with the inputs and outputs. The inputs and outputs, like that. Okay, my output is W. Obviously, since I didn't put a reg here, it means that I'm not trying to assign values to my W output inside always the statements, but I do need always a statement for something. Then I declare parameters. Instead of saying 0, 1, 2, 3, 4, I like to say S0, S1, S2, S3, or give states names. And therefore I use a 2-bit parameter that can give me 4 names for 4 of my states. Okay? Then I need something to hold the current state of my machine, and I declare a reg 1:0 current. Okay? Since I have 4 states, a 2-bit reg is good enough for holding the states of my machine. Then I have an always statement on the positive edge of the clock. Okay? Then on the positive edge of the clock, I'm making transition from one state to another, one state to another. And so this is the parameter part. This is the 2-bit register part. It is a 2-bit register, and this is where transitions are being made. And so let's read it this way. Okay. On the positive edge of the clock, if reset is 1, then your current state becomes S0. This part is described by this. Okay, if reset is 1, current state becomes S0. If not, then look at the current state. If the current state is S0, then if the current state is S0, then if A is 1, your current state becomes S1. Otherwise, your current state becomes S0. What it means is, I'm describing this part. If the current state is S0, I go back to this state. If the current, is 0, I go back to this. If the current state is 1, I go to S1. And therefore, S0 it's a little darker than what I liked it to be. So let's switch to this one instead. So this line corresponds to the S0 state. If the current, the value of current is S1, then if A is 1, I go to current state S2. So let's do this now. Okay. If A is 1, you go to S2. If A is 0, you go to S0. Okay. Next state. S2. If you have a 1, if A is 1, current becomes S2 itself. Otherwise, you go to S3. Here, okay, in S3, A1 takes you to S1, A0 takes you to S0. And therefore, all I'm showing is that very easily you can go from this state diagram to the Verilog description of it, and then again I have the end case here which ends the case statement. I could, if I wanted to, or maybe it is recommended that I also put default, and if it is default, then my current state becomes S0. That means if something wrong happens, go to the initial state. Altogether, this describes my state machine, and I have for each of the states here, I have a line or a case alternative following the edges and the states that I have here. And the only thing I haven't done yet is describing the output of my state machine. The output of my state machine, let's still use another color if I can find something. Okay. I will use an assign statement. Okay, it's too dark. And unfortunately, I don't have any other color. Yeah. Anyway. Okay, this is the output, and this is where the output is receiving the value. Okay, see, read the state diagram at the bottom. It says when you are in state S3, your output is 1. Now I'll read the assign statement. It says output is, if your current state is S3, is 1, otherwise it's 0. So it means that this assign statement corresponds exactly to the this value 1 in my state S3 as output. Altogether, this description has shown you this complete description back here. Okay, this complete description is the description of the state diagram, and I've shown you line by line correspondence or extracting this Verilog description from the state diagram. One last thing before we end, and that is test benches. When I design something, I have to test it. Okay, if I build something, I have to test it. What do you do when you want to test something? Well, you put it on a bench, right? Okay, and then I do the same thing in the virtual world. In the virtual world, I have a bench. Let's say this is my bench, and on my bench, it has 4 legs. Okay. On my bench, I put my, let's say, sequence detector. Okay, on my bench, I put my sequence detector. And then, on my bench, I will have something to generate data for the input, something for the clock input, for the data input, maybe for the reset input. And then I will observe the output on maybe an oscilloscope or something. And therefore, I have a component here, a function generator, maybe a switch for the reset, and then maybe I have a an oscilloscope connected to the output for observing the output. And this is the environment I want to mimic, or I want to model. A test bench is exactly this. Okay, for this whole bench, I will write a Verilog module. And my Verilog module is like this. Module detector tester, or detector test bench, name it whatever you want. I have to have time scale because I need to time my inputs. Okay, the rules for test bench. First, declare the heading. Second, for all the inputs of the circuits, these yellow boxes I'm showing, for all the inputs of your circuit, my test bench became white. Okay. This is the test bench. For all the inputs of my circuit, I declare yellow boxes here. But then for the Verilog, I will use red for all inputs of my circuit. So you are seeing that I have AA declared, clock declared, RST declared as reg, and then giving them value 001 initially. Okay, so what it means is here is a thing that is called AA. Here is a thing that is called clock. Here is a thing that is called RST, and they're receiving their initial values. Okay, so after the header, that means after this white table, okay, and giving it the name, detector 110 tester, detector 110 tester. Okay, then I have this yellow part which declares my inputs. And then somehow I have to observe the output. The output is observed by, let's say, an oscilloscope. Here, a waveform will be showing my output. And therefore, I have to declare a wire that that's that green box in this bench here. I have to declare a wire that carries my output. The name I'm giving it is WW. Okay, so far, this is what I have. The table and the boxes for the input, or the function generator for the inputs, and maybe an oscilloscope for the output. Next, what I want to do is to instantiate or bring in the circuit that I want to test. Okay, so I go and grab my circuit. Now my circuit has different signal names. It has an A, it has a, let's go back here and see what are the names of the ports of my signal: A, CLK, reset, and W. A, CLK, reset, and W. Okay, I bring in my box, the circuit that I'm testing, that happens to be detector 110, and then I have to connect the ports of it to the input function generators, maybe. So I connect this to this, I connect this to this, I connect this to this, and this to this. Okay, and therefore what I have achieved by instantiating this is this box over here. Okay, all right, what now? Well, you took a table, you put your function generators and oscilloscope there, You brought in the circuit, put the circuit there, wired the inputs of the circuit to the function generator and the scope that you have. Okay, now what you do is you have to apply data to your AA, to your CLK, to your reset. I use initial statements for doing that. An initial statement is a procedural statement within which you can have procedural statements, okay? Like wait, like repeat, like if, like loop, like case, and so on, okay? One initial statement generates the clock for me, and therefore, this is the initial statement that generates the clock for me, which is this one over here, okay? The CLK yellow box, which is this one. The way it reads is the following. Repeat 44 times, okay? Repeat 44 times, and then wait 7 nanoseconds. Wait 7 nanoseconds and then complement the clock. What it means is I am generating a clock that has 50% duty cycle and 7 nanoseconds. 1, 7 nanoseconds, 0. That means the period is 14 nanoseconds. For my AA, I'm generating, that's another box there. Let's go back here and look at this. This is the AA box. For the AA box, I'm generating another periodic clock, but this time instead of having a period of 14, it has a period of 46. And then that complements again. So what I'm creating is I'm creating some signals on A and some periodic signal on clock so that various waveforms will be applied so that I test it to see if I can get a 110 on my output. You could be more specific. You could wait, for example, 15 nanoseconds, put a 1 on A, wait 20 nanoseconds, put a 0 on A. You could do that, but then it's easier to just do, let's say, you have periodic data or random data or data such as what I'm doing over here. And then I have another initial block for my reset. My reset becomes 1. Well, actually, my reset is 1 already, but that's okay. It becomes 1 at 31 nanoseconds, and then 23 nanoseconds later, it becomes 0. It means that my reset will be my reset will be active long enough to reset the circuit using the clock, and therefore this in effect is this other box here that I have shown as, let's say, a function generator or maybe a switch or something. Altogether, these provide my inputs, and then how about my output? The output actually is going to be observed on the waveform of the simulation output anyway, but then I can also have an always block to wait for the output to become 1. When it becomes 1, it reports. Display is a way of reporting. A 1 was detected on W at time such and such, and then put the time that W becomes 1, or output the time that W becomes 1. And therefore, this is corresponding to this green box over here. So all in all, what I have done is I have developed the test bench, and the test bench has a table, the white stuff, yellow stuff for the inputs and output, or the ports or things that connect to the ports, and then the detector instantiation. Notice that I'm doing connection by port connection, ordered port connection, means AA connects to A, clock connects to CLK, RST connects to reset, WW connects to connects to the W output. And then this is the table that I have, okay, which corresponds to that test bench. I will run this, I will run the simulation, and the simulation will give me some waveform that I can check to see whether my detector is working properly or not. And so like I said, this is just the tester. It has the input-output declaration, it has the instantiation, and then it has the data application, which I'm showing over here. Okay, just going through this so that you have these bubbles to read through. Okay, reset becomes 1. It's already 1, so it stays 1 beyond 31 until 23 nanoseconds after that. Then it becomes 0, and then let the circuit perform its regular operations. And then this is where you report your output. This is sensitive to the output W. That means anytime W changes, come into this, and then if it is 1, then report. Okay, finally, what we have done, we have gone through a little bit of RTL, then showed some constructs of Verilog. A multiplexer was used for showing various forms like gate description, Boolean expression, conditional expression, and always a statement. And then following that, we have gone through the data path components, several of them, like a shift register, like an ALU, like a counter, and all that. And at the end, what we did, we covered a sequence detector that represents the way we will describe controllers for data for RT level design. And then we developed the test bench for the controller to show the concept of test benches. Okay.